Here, since the expression on the right hand side is the sum of n random variables, therefore, the limit here refers to one of the mode of convergence of a sequence of random variables, that is a limit in the sense of probability in distribution almost surely or in orth mean. When we can say the Ito integrable, whenever we have a stochastic process is Ito integrable, it has to be adopted, that is measurable, as well as it should be a mean square integrable. If these two conditions are satisfied, then you can say the stochastic process is Ito integrable. And the Ito integral, which we have discussed in the first line, I of t is equal to integration 0 to t x of u dwt. So a stochastic process is called the Ito integrable on the interval 0 to t if it satisfies the first condition is it's adopted, that means x of s is f of s measurable, and it is mean square integrable, that is integration 0 to t expectation of x square s ds has to be finite. Now we are going to discuss a few examples. Through that we are going to study the Ito integrals. First we consider the simple situation. Consider the Ito integral for a simple integrand function. That means, for example, you can see the illustration with the price may be negative. Let Wt be the price per share of asset at time t, and xt be the number of shares taken in the asset at time t, and ta be the trading dates of an asset. Assume that xt be a simple process. That means it takes a constant value in the interval ti to ti plus 1. The gain or loss, there is a possibility the price may go down and so on, maybe negative also. So with that assumption, the gain or loss from trading at each time can be viewed as a I of t, because I of t is nothing but integration 0 to t x of t dwt. Therefore, the gain or loss from trading at each time can be viewed as a I of t. So since it is a simple process, you can write it x of t comma w, where w is belonging to omega. You can write down the simple process in this fashion, where psi a be the bounded random variables such that psi naught is f naught measurable and psi a's are f ti minus 1 measurable. Because it is taking a constant value between the interval t, it takes a constant value between the interval ti to ti plus 1. Therefore, you can write down the simple process x of t in this form. So for a simple process x of t, the stochastic integral I of t, that is nothing but the gain or loss, that I of t is nothing but the integration 0 to t x of s d of ws, that is nothing but limit p tends to infinity of I is equal to 1 to p psi I multiplied by the difference of wi's. In this limit, the first term of the above equation, that is psi naught pi naught y indicator function of t, does not contribute anything, hence w naught is equal to 0. In particular, if you take x of t is equal to 1 for all the interval, then the psi a is equal to 1 for all the interval. Therefore, the I of t is nothing but, since x of t is equal to 1, you are just integrating 1 with respect to ws. Therefore, you will get wt. We calculated Ito integral for a simple integrand, as a general integrand can be expressed as the limit of simple integrands. Therefore, the Ito integral of general integrands can be obtained by taking the limit of sequence of Ito integral of the simple integrands. This is a simple situation in which integrand is a simple function. Suppose the integrand is a deterministic function, not a random. The delta t is not a random. Now we are defining the Ito integral I of t, that is 0 to t delta of s dws. Since expectation of I of t is nothing but a I of 0, that is equal to 0, because the Ito integral satisfies the martingale property. This we are going to discuss at the end of this lecture. The Ito integral is going to be a martingale. So this property is used here. Otherwise, we can directly find out expectation of I of t, that you will end up 0, or by using the martingale property it will be I of 0, but I of 0 is equal to 0. You can find out the variance of I of t also. For that you have to find out expectation of I square of t, that is nothing but expectation of 0 to t delta u of dws. Then you can find out the expectation of I square t, so that will end up delta square of s ds. So using this you can find out the variance. Variance is equal to expectation of I square t minus expectation of I of t whole square. Since expectation of I of t is equal to 0, therefore variance of I of t is same as expectation of I square of t, that is 0 to t delta square s ds. Or you can use the isometric property for finding the expectation of I square, that is same as 0 to t expectation of delta square s ds. Since delta t is a non-random function, the expectation of delta square s is same as delta square s. So one can use the definition and find out this expectation, or you can use the isometry property and use the expectation of a constant is same as a constant, therefore it is 0 to t delta square s ds. So in this example we are finding the expectation and the variance of I of t. But you can find out the distribution of I of t also. You can find out the distribution using moment. So find out the moment generating function of I of t. You know that a moment generating function for any random variable is nothing but expectation of e power u times x. So here you are finding the distribution of the random variable I of t for fixed t. Therefore, it is expectation of e power u times I of t. You can find out that this value is e power of times u square integration 0 to t delta square s ds. So once you are able to find out the moment generating function for fixed t, you can compare the moment generating function of some standard distribution. Then you can conclude what is the distribution of I of t. Here the moment generating function is e power of u square integration 0 to t delta square s ds. So this is same as the moment generating, this is of the form the moment generating function of normal distribution. Therefore we can conclude for each t, I of t is normally distributed with the mean. Now you have to compare this moment generating function with the moment generating function for function of normal distributed random variable with the mean mu and variance sigma square. By comparing the MGFs, you can conclude what is the mean and variance of I of t. So here you will come to the conclusion the I of t is a normal distributed random variable with the mean 0 and the variance is integration 0 to t delta square s ds. For fixed t, it is normally distributed. So in this example, we are finding the mean and variance of I of t as well as what is the distribution of I of t also. We are finding the mean and variance as well as the distribution of I of t when the integrand is non-random function, of time. Third example, here we are evaluating the integration 0 to t, integrand is w of 1 dwt. Note that w of 1 is not adapted to the filtration, that is f of t. Sigma of ws for the interval 0 to 1. As the t increases from 0 to 1, w1 is not adapted to the filtration f of t, where f of t is the natural filtration of linear process. So since it is not satisfying the condition of integrand is adopted, therefore this is the Ito integral does not exist. So this example shows that the assumption of integrand is adapted to the filtration is needed to have the existence of Ito integral. So here the Ito integral does not exist.